Hello, Sujata ma'am.
Sulma.
Are you able to hear?
Yeah.
YouTube has started.
Okay, good.
It is live.
Let me check it. One second.
It's on, ma'am.
Lavana?
Yes, sir, it's working,
Can
sir.
you forward that Zoom link to the MC, what is that, Rishika, I think. She has not received.
Let me check it.
Will do.
Rishika and as well as that Subhashri. Ma'am, it is on.
Yes, pa. I checked it is on.
The team of RI have joined. Adil Mohammed.
Three more have to join, sir. They will be joining in 2 minutes.
Okay.
Yes, sir. We're waiting for them.
Okay, fine. Rishika?
Yes, sir.
Are you able to unmute?
Yes, sir. I'm able to unmute.
Okay. So, what about this Subhashri?
She'll be joining soon, sir.
So you're planning to turn on your video?
Yeah.
Ma'am, actually the plan was to turn on the video. All of a sudden my system got crashed. So I'm coming in my phone, ma'am.
Okay, but you can turn it on in the phone also, right?
Also, right.
Yeah, ma'am, but the content is in the phone, that's what.
Okay, so but you can't your laptop is not working, is it?
Yeah, ma'am. So if it starts working before 6, I'll just open the content in my laptop.
Yeah, but it won't look good if you just speak
ma'am.
over without turning on your video.
Okay, ma'am. I'll see through it. I'll do something.
Okay, but don't panic. It's fine. Yeah.
Okay, ma'am.
Team Savita has joined. I think one person has joined.
Samreen from Savita, I think. Team Samreen.
Okay, I think Dr. Sendel Kumar has joined. Good evening, sir. Dr. Sendel Kumar, sir. Now you can able to unmute yourself.
Hello, sir.
Sir, yes, sir. Good evening, sir. Welcome, sir.
Good evening, sir. Thank you, sir. Robin, sir.
Yes, sir.
Sir,
And
good evening,
Lavana
sir.
and Sujata ma'am also is there.
Okay.
Hello,
then.
Sendel sir. Lavana here. Good evening,
Hello,
sir.
madam. Lavana, madam. Sujata, madam. Good morning. Good
Good
evening, madam.
evening, Dr. Sendel Kumar. நல்லா இருக்கீங்களா?
நல்லா இருக்கா, madam? நல்லா இருக்கீங்களா?
I am good, sir. Welcome to the
Okay.
program. Thank you for being the host.
Ma'am, no problem, ma'am. Because of you only everything is happening, madam.
என்ன
It's
சார்
great
எங்க
growth.
கையில ஒண்ணுமே இல்ல, நீங்க எல்லாம் பண்றதுனால தான் we are all doing something. Anyway, உங்களோட
நாங்க-
voice is a little feeble. நீங்க கொஞ்சம் டிஸ்டன்ஸ்ல இருந்து பேசுறீங்களோ?
இப்ப கேக்குதா?
இல்ல
இல்ல,
கேக்குது, பட் a
but
little
ரொம்ப
feeble இருக்கு. கொஞ்சம்
பக்கத்துல
டிஸ்டன்ஸ்ல இருந்து பேசுற மாதிரி இருக்கு. மைக்ரோஃபோன் பக்கத்துல இருந்தா it will be better.
மைக்ரோஃபோன் பக்கத்துல தான் madam இருக்கு. மேம் இப்ப கேக்குதா?
கேக்குறது சார், அப்பையில இருந்து கேட்டுட்டு தான் இருக்கு. பட் ஆனாலும் கொஞ்சம் ஒரு கணத்துக்குள்ள இருந்து கேக்குற மாதிரி இருக்கு.
ஐயோ. இப்போ மேம் கேக்குதா?
fine.
Fine, sir. Yeah.
Fine.
Ma'am, can you able to hear me clearly?
Yes, sir. But ஆனா என்ன கேட்டீங்கன்னா பெட்டரா இருக்கலாம். என்ன ராபின் and how do you feel?
It's some little bit feeble, sir.
Little bit.
Voice.
Ma'am, Robin sir.
Yes, sir.
Ma'am, are you able to hear me
Yeah,
clearly?
yeah. Yes, we can, but the voice is very low. So you are using a microphone or?
Yeah, microphone only, sir.
That then hold it your this one the speaker is.
நீங்க கொஞ்சம் வாய் பக்கத்துல இத வெச்சுக்கோங்க அந்த போன் மைக்க.
அப்பதான்
இப்ப கேக்குதா? இப்ப கேக்குதா?
This is much better.
Much better, huh?
ஆமா.
என்ன சென்டர்லயே?
Robin sir. Hello,
Yes.
sir.
Yes.
Sir, can you just tell me if I'm visible?
Yes. Yours, Subhashri?
Rishika, sir.
Rishika. Yes. We can see you.
So, you can still wait, sir, 1 minute. Am I still visible, sir?
No, Rishika. Now you have to switch off your video.
Okay.
Sujata madam,
Earlier we can able to view.
Sir, சொல்லுங்க sir.
இப்ப கிளியரா கேக்குதா ஓரளவுக்கு?
கேக்குறது sir. It's better. I mean, I won't say it is very great, but it is fine.
Hello. Okay வா?
கேக்குறது sir.
Okay. Then fine.
உங்க வீடியோ வேணா டர்ன் ஆன் பண்ணிக்கோங்களே.
Good evening, Arun Dev sir. Are you able to unmute yourself? Arun Dev sir?
Coming.
Yeah, fine.
Okay. Sujata, hi, Lavana.
Hi, Arun.
Hi, sir.
மேடம் வீடியோ டர்ன் ஆன் பண்ணிட்டேன். ஆனா வீடியோ வர மாட்டேங்குதே.
I think you had your video on, Dr. Sendel.
I have switched on the video, sir.
No. When I first came in, I saw your video, but then now you have probably switched it off. Just check that. I don't know.
Okay. I'll log out and I'll come in, sir.
Okay. Thank you, sir.
Good evening, Dr. Yogesh Kumar Sinha. Hello.
Can you hear me?
Yes, sir.
Yeah. Good evening.
Arun Dev sir, that Dr. Yogesh Kumar Sinha from Rajalakshmi, HOD Affair of Department.
Hello, sir. Good afternoon. Good evening.
Yeah, good evening, sir.
Thank you for joining, sir.
Robin, you have to be a bit louder as well. You're actually swallowing the last few words. I didn't
Okay.
hear you. Dr. Yogesh
Yogesh
Kumar is
Kumar Sinha.
who's the
He's
faculty?
a
I sorry.
HOD. Yeah, Rajalakshmi, HOD of Aero department.
Okay. Welcome, sir. Welcome.
This is
Thank you, ma'am.
Sujata.
Thank you.
So, Robin, sir, could you hear
Your voice is feeble.
me?
Who is that? Rishika?
Shubhashri, Shubhashri. It's breaking,
Shubhashri?
Shubhashri. We can't
Yeah.
hear you.
Is it better now, sir? Subhash,
Yeah, better, but still.
I'll just, unmute myself again, sir. Give me a minute, sir.
Robin, I'll go on mute. You don't need to call me out now.
Okay, fine, fine. Dr. Sendel Kumar, sir, now you can unmute.
But my video is not coming, I think so. That's the problem. I don't know. Today morning also it came, but
Maybe the connectivity issue or internet.
No, while switching on, we could able to see a black screen alone.
Yeah, blank screen.
Start
Correct.
my video instance. Co-host has stopped your video. They are given, sir. Co-host has stopped the video. They are given.
Okay.
Intimation. Co-host has
think...
to unmute me to post my video.
No, sir. That you can switch on because I have given the same rights to other participants also. So you can.
But it is not coming now.
It's still.
I don't know why it is so.
Arun sir, CNC is joining.
Yeah, he might come in a little late, Robin.
Okay, fine.
Sir, can you try login with some other device?
Try, yeah. You can try with.
Ma'am?
This is Rishika.
Yeah, ma'am, this is Rishika.
Yes, Rishika.
Bashri?
Bushri has joined now.
I think she had some problem.
Lavana, that Sona team has not joined it, I think, because.
I'll try them, sir. I'll pick up with one.
Sir, Subhashri here says my voice audible.
Yeah,
yes.
Very clear. Good.
Yes, sir. Thank you, sir.
Subhashri.
Yeah?
There's some problem with my system. I won't be able to turn on the video.
Even I don't think I can turn on the video. I have a very poor network system here.
Okay, cool then.
Yeah.
I think from Savita, all team members are in. RI also.
Yes, sir.
Sona only is there.
Sorry, am I audible still?
Yes.
Okay.
CNC is there.
No, Sujata, he said he'll join a little late.
But I see
He
CM
joined.
Chandra.
He joined. Yes.
And I see Dr. Sendel Kumar also not on co-host. Can you check?
Done,
Dr. Philip Praveen is there. Mr. Philip Praveen is there. Can you also make him a co-host? And can you also check from RI?
Good evening, sir.
Good evening. Good evening.
Good evening.
Check Dr. Philip Praveen is there.
Arun Dev, sir. Mr. Philip Praveen is joined.
Yeah. Good evening. Good evening, Philip.
Good evening. Good evening, sir.
Dr. Sendel Kumar, can you switch on your video now? You can check.
Sir, it is already switched on only, sir. But it's not coming. For so many of them, the same issue.
Fine.
Excuse me, sir. Sendel, sir.
Yes, ma'am.
Unmute.
Sir, I'm Samrian, sir. Can you make Sandhya a co-host, sir? Because she has to share the screen, sir.
What's her name?
Sandhya, sir.
Sandhya.
Yeah. Thank you, sir.
Done, ma.
Thank you,
Robin, sir. Robin,
Yes,
sir.
Yes, sir.
ஏன் சார் வீடியோ வர மாட்டேங்குது? போட்டோ மட்டும் தான் வருது. யார்?
CNC?
சார்?
No. CNC.
Sir, whether I am audible?
Yes,
sir.
We can hear you, sir, clearly.
Yeah, fine. It's already time, I think so.
Yeah.
Vivek has not joined.
Robin.
Robin, sir, can you check? Philip sir has said Abai sir has joined.
Good evening, Dr. Vivek. We can say it is good morning to him.
Actually, in US it is good morning.
Yeah, good morning.
Yeah, good morning.
Robin, sir, kindly co-host Abai, sir.
Yes.
Okay. All right.
Hi, good morning, Vivek.
Good evening. Good evening.
Sir, good morning, sir. Vivek, sir.
Good morning. Good morning. How are you?
Fine, sir. How are you, sir?
Very good. Thank you. Thank you.
Welcome to the section, sir.
Thank you. Thank you very much.
Good evening, Dr. Abai Meghnath. Welcome, sir.
Thank you. Good evening.
Dr. Vivek, you can share your presentation. So I have stopped sharing the banner.
Okay. Very good.
Sir, do we have Sona College?
Let me bring up my presentation and share it.
Yeah, Vivek, we have a few introductions in the beginning before you start off. So you can just put on your screen and then we get it.
Okay. Yep. Do you want me to share my screen or are you?
Yeah, you can share it. You can share.
Okay. Let me try sharing it. Let me know if you see it. Can you see it?
Yes, you can put it in the slideshow.
Okay.
Yes, Robin, I think.
Okay.
Yes, shall we start, sir?
Yeah, go ahead.
Yeah.
Good evening, one and all gathered here. I am Robin from the PALS Program Management Office. PALS Campus Event Acquire Session on Deep Technology hosted by Savita Engineering College and Rajalakshmi Institutions. I would request the MC of the day, Subhasri Priyadarshini and Rishika, to take care of the proceedings. Thank you.
Thank you, sir. A very good evening to everyone present. I'm Subhasri Priyadarshini from Savita Engineering College, and we have Rishika Krishna from Rajalakshmi Engineering College. We are going to be your MCs for today's session. And attention participants, I request all of you to kindly mute your mics and switch off your videos. And register your attendance in the format of abbreviation of your college name, hyphen, your name, hyphen, student or faculty. I repeat, attendance in the format of abbreviation of your college name, hyphen, your name, hyphen, student or faculty. And also, don't forget to fill in the feedback form and quiz, for which the link will be provided by the end of the session. Now, I invite our PALS champion, Mr. Arun Dev, to welcome everyone who has joined us today. Please, sir.
Yeah, thank you. Good evening, everyone. Thank you very much for joining us for this session on deep technologies. Special thanks to Dr. Sendel Kumar from Savita and Mr. Abai Shankar Meghanathan for finding time to join us for this session. The Acquire sessions are basically to give students an overview on deep technologies. When you read some of the new books on what are these deep technologies, there are probably 10 of them which have potential for exponential growth. It is our focus to try and bring as much of this to the overview of students so that they're able to get an exposure and probably develop their interest on all these events. all of you may have heard about PALS. I don't want to take too much time explaining the background about PALS. This is our 20th event in this year. So I'm sure a lot of you have heard about us. Without much ado, I'd like the MCs to take this forward with the introductions from the two college heads.
Thank you for your kind words of welcome, sir. I'm honored to introduce Mr. Abai Meganathan, a dynamic and a young educator, very well in business family with great interest in education. Vice chairman of Raj. As part of the senior leadership, he provides vision and strategy for the overall growth and development of the institution. He has been responsible for scaling up the infrastructure in the campus and making the campus more student-friendly. He has also been responsible for several path-breaking and innovative process changes that has helped the institution maintain its high growth trajectory. Mr. Abai also heads the retail business of the Rajalakshmi Group in both passenger and commercial vehicles. Under his leadership, the automobile retail division has been recipient of several awards from Maruti Suzuki India Limited. Rajalakshmi Wind Energy, under Mr. Abai's leadership, not only produces 180 megawatts of clean wind energy, but also is getting ready for a major expansion to increase the installed capacity to produce 500 megawatts of clean energy. Mr. Abai is also an avid golfer with a number of awards and laurels to his name. He always keeps tabs on various management volumes and constantly develops his entrepreneurial knowledge. He looks forward to learning something new every day and believes in challenging himself to make him a better person in all aspects. He holds an UG in Electronics and Communication Engineering from College of Engineering, Guindy, and an MS from Cyrus University, New York. I now invite Mr. Abai Meganathan to give his host speech. Please, sir.
Thank you very much. Thanks for the lovely introduction. Very good evening to one and all present here, from Dr. Vivek, Dr. Sendel, and everyone from the PALS team. And all the students and faculty members who have come here to listen to Dr. Vivek speak about intelligent systems. I think we have been hearing a lot about Industry 4.0 and the fourth industrial revolution that is coming towards us, or rather we are going towards. And we are trying to adapt ourselves in various ways, and these kind of forums really help us bounce ideas, get newer ideas, and tune ourselves towards being better prepared for Industry 4.0. They say cyber physical systems form the basis of the Industry 4.0, wherein a cyber physical system is a computer system where a mechanism is controlled by computer-based algorithms. And this definition alone gives me gives everyone the importance of interdisciplinary learning, where we from an educational institution's perspective, we have there is a continuing mindset that there is a resistance towards interdisciplinary learning, because it kind of goes ahead against the traditional departments, and the mechanical engineering is different compared to electronics and computers, so on and so forth. So this mindset definitely has to change, and I hope people buy into this idea, and people look towards engineering and technology as one rather than multiple disciplines of engineering. Me personally, I really look forward to one area of Industry 4.0, which might be very, very important to India as a country, and more specifically Tamil Nadu, is smart grids. I feel that is an area where technology has to change the way we govern ourselves, how our society is being governed, because this is one area where we are far behind a lot of the developing world as well. We have progressed well on mobile telephony, on many such technologies. We have the best of cars running in our roads. We have a lot of things, which the Western world and the other parts of the world can look to us. But electricity, for instance, where we're trying to serve a country of over 1 billion people, and we're trying to electrify the entire country now. And from what I hear, we've all come very close to doing that. But are we doing that efficiently? Are we doing that without loss of power, without loss of revenue, without without too much of damages? Today, maybe we are not doing that, and something like a smart grid, which if we are able to adapt throughout the country, we will be covering these topics more efficiently. And to this, I would I'm trying to work in the REC to work on some microgrids to show that within our locality, we will be able to create an efficient system of power distribution with minimal loss of power and with very little with great cost savings. See, today we're looking at a distribution entities in the country which are extremely in the red. They're heavily loss making because of the lack of efficiency. And this kind of technology has to change the way we govern ourselves and push the people who are governing us to adapt these technologies. At REC, we're trying to. Our main focus is to adapt our curriculum to the changing needs. I think that was something that we spoke about a lot earlier, maybe 5-10 years ago, and now we're able to do that more because there's a bigger buy-in. There's a greater buy-in from students, academicians, and industry experts about the need for an actually dynamic curriculum, which we're able to do today. And I'm really thankful to my colleagues for trying to be as updated as possible. While changing the curriculum is one part, the other major part that we really need to understand is the faculty development towards an ever-changing curriculum. To which, again, coming back to PALS and organizations like PALS become a big support in trying to update our faculty members to update themselves in the latest industries, latest technologies, which we want to further to our students. Without too much of time, without taking too much of time, I would thank PALS again for having us, for letting us host the Intelligence Systems Seminar with Dr. Vivek Badami. And I'm looking forward to hearing from Dr. Vivek. Thank you so much.
Thank you
for your informative talk, sir. It's a privilege to introduce Dr. Sendel Kumar, the Vice Principal of Savita Engineering College. He has completed his PhD in the field of DC to DC power converters in the year 2013 from Anna University. He has a total of 23 years of experience in teaching and a year of industrial experience. His passion is to teach the subjects in a practical and industrial-oriented approach which will make the students interested in the subject and also self-motivated to become future entrepreneurs and good citizens of India. He has published 12 research papers in reputed international journals and 5 papers in international conferences. He has got Best Teaching Award in Engineering by Staffordshire University, UK, and Educational Matters in the year 2014. He has also written the book named Special Electrical Missions in the year 2009 and has been the reviewer of many books and journals. He organized and conducted many international conferences, faculty development programs, technical workshops, seminars, and many more. He visited countries such as MDIS University Singapore, Taylor's University Malaysia, and delivered conference lectures on electronics engineering, smart agriculture, and special missions in industries. He has been one of the academic council member for a reputed engineering college and holds membership in IEI, ISTE, IEENG, UACEE as a life member. He has been an active executive member of Savita Engineering College for PALS since 2019. I now invite Dr. Sendel Kumar to give his host speech. Please, sir.
Thank you very much for the introduction. Can you able to hear me?
Yes, sir. Go ahead.
Yeah. Very happy evening to everybody else. It really gives me an immense pleasure in addressing the gathering. On behalf of our management, principal sir, myself and faculty members and students, I extend a very warm welcome to the today's speaker, Dr. Vivek Badami from US. At this moment, I should extend my welcome to Abai Meghanathan from REC also. In this moment, I thank PALS team for giving us a great opportunity to host this Aqua lecture series on AI and its control. We, Savita Engineering College, is associated with PALS since 2019 onwards, and our management is very, very happy such that the faculty members and students are benefited and exposed to various latest technologies through this various programs conducted by the PALS, such as Aqua Aspire lecture series, as well as FDP's workshops. In the last year, PALS has conducted many programs in the queue, such as this kind of lecture series, technical workshops, FDPs for faculty members as well as for the students, IVs, online quizzes, and T2P program is one of the important thing where the students are like very much, as well as faculty members like very much for students as well as the faculty members. Particularly, the students were very much interested and involved in PALS Innova project competition. Really, at this point of time, I should give a hats off to the PALS team for organizing PALS Innova project competition last year. Similarly, this year also, they have started their journey. Under pandemic situation also, they are working very hard to organize the programs as per the schedules, and they are working a very difficult manner to organize all those programs, including all the guest speakers. They are successful too. Again, one of the important programs for this year, till now, as per my idea is concerned, VLab initiative and training for the faculty members. Again, really going to be helping all the partnership colleges in doing the VLab virtually for the students. This is the pandemic situation. Everybody knows this one, because VLab is going to be a future laboratory experiments conduction process where all the colleges have to involve themselves. At this moment, I want to thank a few members of the PALS, Arundev sir, Mohan sir, Krishnamurthy sir, Anu ma'am, Sujata ma'am, Robin sir, Chandrasekhar sir, Lavana madam, Subramaniam sir, and other peoples of PALS for their tremendous effort in organizing the PALS event. Again, today, at the current scenario, we have got three important buzzwords. One is AI, second is ML, and third is DS. AI is under artificial intelligence, machine learning, and data science, which are going to play a very major role in industry automation sector and also in software development fields. These three topics will be very common to all the engineering disciplines. For example, AI in power systems or the smart grids is very important one. Designing of CNC using the ML and data interpretations, robotics, all those things comes into picture under the AI and ML and DS. So today's lecture is going to be a very eye-opening section for everybody else in AI and its control, given by the expert Mr. Vivek Badami. Let us all benefit out of it. Thanks for the opportunity given to me by PALS. Jai Hind. Thank you very much.
Thank you, Dr. Sendel Kumar.
Thank you for a very warm talk, sir. However difficult life may seem, there's always something you can do and succeed at. Success is the progressive realization of predetermined, worthwhile, and personal goals. I'm immensely happy to introduce the speaker of the day, Dr. Vivek Badami. He worked in GE for a total of 35 years, most recently as a consulting engineer with GV Aviation in the Boston area, retiring in 2019. He was responsible for advanced sensor strategies and prognostics and health monitoring for aircraft engines. His previous roles in GE included 14 years in power generation and 16 years at GE's Global Research Center in Schenectady, New York. Prior to GE, he worked for Computer Vision Corporation and Digital Equipment Corporation on CAD/COM automation, processing, real-time system, PHM, artificial intelligence, and control in a variety of industrial application areas. Primarily power generation, robotics, and automation. Vivek has a PhD in controls and Reservoir Polytechnic Institute, specializing in the application of fuzzy logic to control. A master's in electrical engineering from the University of Rhode Island, specializing in the vision-based robotics, and a bachelor's in electrical part from IIT Madras in 1975. Vivek is a holder of 500 patents, authorized 15 publications, and has received numerous awards for technical excellence during his career in GE. He is a senior member of IEEE. He is currently focused on teaching topics related to sensor-based system and monitoring. We welcome you, sir. Now I request Dr. Vivek Badami, Speaker of the Day, to present the session. Please, sir.
Thank you. Thank you very much. Can you hear me?
Yes, sir.
Yes, sir, we can hear you.
Okay. Thanks for that introduction. Just a quick correction. I had 50 patents, not 500. So I wish I had 500. But thanks very much for the invitation. I really am honored to be here. Thank you for inviting me. What I'd like to do today is present a little bit about the so-called intelligent systems, which is a very fast-moving field that combines AI, controls, sensors, actuators, and so on. And one of the reasons I'm interested in this whole field is it's, first of all, of course, intellectually very exciting, but also I think it's already happening. Intelligent systems are already with us. I think everyone has heard about the stunning, growth of AI. But what's maybe not as well recognized is that AI is actually permeating and getting into the whole field of physical systems. And that's the area I want to focus on. Just as at the outset, this is not going to be a totally detailed deep dive into any particular technology. By design, I just wanted to give you a broad overview of the field. And I hope that's okay. And you can get a general feel for the broader trends in the field. So the outline I'm going to follow today is to give you an overview of artificial intelligence systems, focus mostly on the real-time embedded autonomous versions of them, a little bit about the architecture. I also would like to highlight the parallels to the biological world because that is where we draw a lot of our inspiration from. Mother Nature has been building intelligent systems for 2 billion years. So there's a lot to learn from her. I'd also then talk about the technology drivers and then something about the complexity and risk management because that's a major issue with intelligent systems. So this is going to be more a nuts and bolts engineering overview. I'm an engineer. I'm not a computer scientist. So I'll of course talk about computer science, but this is more looking under the hood, so to speak, and give you an engineering perspective of how these systems are actually built. So before we get too far, we should define what we mean by intelligent systems. And there are obviously a lot of definitions out there. I think everyone has a slightly different definition, but generally most people agree that intelligent systems are technologically advanced machines that perceive the world around them and react somehow. And that's kind of the working definition that I'm going to take moving forward. Before I get into the details of the technology, I'd like to give you some examples of what we mean by intelligent systems. I think one of the most obvious examples is the self-driving car. I think most people have heard about the stunning developments here. And 5 years ago, I think even I would not have dreamed that it would have advanced this fast. And if you look at this picture, you have wireless communication, you have radar, ultrasound, vision, LiDAR, all of them being fused together into, in the computer's brain, localization from GPS, path planning, and control. So all of these are, all happening in real time. There are many, many other examples. Of course, some of the most prominent examples today are autonomous systems, robotics, mainly. So we have industrial applications, inspection robots, mobile robots, consumer robots, farming robots. The field is exponentially growing. one of the amazing developments has been in mobile robots. I wanted to point out a couple of notable examples. There's some stunning developments going on in MIT. These are called cheetah robots. And if you have some time, if you want to Google it, there's some very interesting YouTubes. I want to play you a quick snapshot of a robot from Boston Dynamics, which illustrates the power to weight ratio and the dexterity that some of these advanced machines can operate, can do. So let me play this. I hope it works. We'll see how it goes. So you can see some of the moves here are, it would be something that only a seasoned athlete could perform in the human world. So that's, it's actually pretty amazing. The other area I wanted to talk about are consumer products. There a lot of intelligent systems are now being introduced into even simple things like home appliances, smartphones. Of course, we have a tremendous amount of technology incorporated into smartphones, and social robots such as Google Home or Alexa or things like that. One of the examples I wanted to mention here was you don't need to actually just talk about super advanced systems. There are some pretty simple applications such as consumer robots. Here's an example of a vacuum cleaner robot, and many of these are being sold across the world. This is called Roomba, and one of the things I'd like to point out is this robot actually has very few sensors, and what it does is it, as it goes around the room, cleaning the room, it starts making a mental model of where it is and then using that model to optimize its future motion. So it's a self-learning system. So this is an example of a bottoms-up learning system with very simple rules that can generate some pretty complex behavior. So before I move forward, I'd also like to define a couple of more terms, real-time and embedded. Real-time system is a time-bound system, and its basic requirement is it must keep up with the real-world application it serves in. So for example, a self-driving car has to be able to instantly avoid pedestrians or come to a stop. It can't think about it and make its decision in whatever time frame it feels like. Embedded systems are essentially computer hardware systems that are designed for specific functions. So if you have a vacuum cleaner robot, for example, that I just showed, it actually is focused on just one task, which is cleaning. And so it can't do other things. And these are the two sort of trends that are in these so-called physical intelligence systems that I'll be talking about. And embedded systems are plentiful. There are just literally thousands of examples. The Apollo rocket had a guidance computer, which could be called an embedded system. Cars have control computers. Engines have engine controllers. So there are just literally thousands of examples. So let me now step back a little bit and talk about some common definitions of artificial intelligence. There are many, many definitions. I'm not going to read through all of them. I'm showing a couple of them here. One of them that's interesting is this thing called the Turing test. It was developed by a computer scientist in the 50s called Alan Turing. And the concept is that if a person C is acting with two entities and she doesn't know who's who, it could be a computer or it could be a human being behind a wall. And all she can do is send questions and receive answers. And if she cannot figure out from the answers who's who, which is a computer and which is a machine, then the machine is said to have passed the Turing test. This is an interesting definition. So the definitions, as you might have noticed, all center around simulation of unlike intelligence in computers. So one of the things I want to point out, and this is, I think, more an intellectual discussion, is that intelligence is all around us in the natural world. So far, we have always assumed that only intelligence is the, what we define to be intelligent. That's human beings and the anthropocentric view of intelligence. And there's a linear progression of intelligence from lower life forms to us. And this is completely wrong. Life, even the simplest forms of life exhibit complex structure and behavior, just from the structure of a shell, the self-repeating structure, to plants that can, perform fairly complicated actions like responding to light and competing with predators and things like that. And even single-celled bacterium that can go towards food, away from toxins, and so on. So the simplest life forms exhibit complex structure and behavior. So intelligence is actually manifested at every level of living entities. So let me talk about the focus of my talk today. If you look at AI, there are generally two groupings of AI, what we call narrow AI and general AI. In general AI, the focus is on systems that can do pretty much everything that we do, humans do, solve problems, interact with the real world. And this is generally the stuff of science fiction. It really is not here today. We don't really have general AI or super intelligence in artificial systems. What we have today is more what we might call narrow AI. And these are computational systems like intelligent assistants, game-playing robots, game-playing machines, machine learning, artificial vision, that are very good in a very narrow domain. Today my focus is on physical systems. So things like smart cars and rovers and smartphones. So the focus for my talk today is intelligent systems I'm defining as AI systems that interact with the physical world. So one of the things I want to follow through this presentation is a framework for talking about this whole field, and it's called the see, think, do cycle. And this is a very common paradigm for AI systems that interact with the real world. So I'll go through each of these 3 steps during the course of this talk. So where does this all start from? So one of the starting points for the discussion on intelligent systems is cybernetics. There's a theoretician and pioneer at MIT, Norbert Wiener, who is sort of credited with being the first one to theorize that all intelligent behavior is a result of feedback mechanisms that could be simulated by machines. And so cybernetics is a subset of the larger field of AI. And it refers to systems that are either partially or completely autonomous. And I should mention that the many other theoretical frameworks for AI, biophysics of neurons, computational algorithms, theory of learning, but we'll just focus on cybernetics for now. So there is a basis, there's a theoretical basis for this field called cybernetics, and it's essentially closed loop feedback control. So if you look at this system, this is pretty much 90% of all the industrial controls that we see in the world follow this closed loop. So you have an input, which is a command. You have a feedback signal, which is generated by a sensor that tracks the output, which generates an error signal, which goes into a computer, a controller, which generates an actuating signal, which does something. So everything from thermostats to robots, pretty much at the level have some set of closed loop control systems. And so it is the core of most intelligent systems. So I wanted to get a little deeper for a few minutes with a certain type of algorithm called PID, or Proportional Integral Derivative Control. And this is an algorithm that's used in probably in 90% of the industrial controllers in the world. And the concept is that the error signal is multiplied by 3 gains, which are then added and sent as a control command to the plant. And by changing those gains, the PID gains, you can generate different kinds of behavior. So I wanted to play a little video next of a wonderful example of how you can generate behavior just with a simple PID control. Just want to mention that the researcher here is talking in Japanese, but there are English subtitles, so don't worry.
Robot creator Masahiko Yamaguchi has demonstrated a robot which can balance, steer, and correct itself while riding a fixed gear bike.
特徴はですね、このロボットが自分自身の足でペダルをこいて、ハンドル操作のみによってバランスをとる。これはおそらく世界で初めてだと思います。当初人工知能に興味がありまして、その中で知能と技能はある意味等価であるという発想でですね、技能の側から知能に迫りたいというのが目的です。で、そのためになんか適当なものはないかなというふうに考えてましたら、近くの科学技術館にですね、自転車ロボットの実演がありまして、それを見て、これをその技能として取り上げたいなということで、自転車ロボットを作ってみようということになったわけです。
This robot system consists of a commercially available bipedal robot and a bicycle made by Mr. Yamaguchi. To detect how much the robot is tilting, the Tag 201 gyro from Tamagawa Seiki is used.
Anyway, if you're interested, you could go through this, and it's pretty amazing how you can generate complex behavior from very simple algorithms. And intelligent systems basically build on this concept. So because of increased computational power, more sophisticated sensors and actuators, this whole thing is just exploding. You can think about all the different pieces, the 3 different pieces here, increasing in their capability because of technology. So just wanted to again mention that we cannot claim ownership of feedback control systems. Mother Nature has been doing this for at least a billion years or so. And the natural feedback control system is called homeostasis. It's nature's feedback control system. And shown here is one example in the human body of how we control temperature, our body temperature. And just like this, there are at least 16 other closed loop systems that are continuously going in our body unconsciously. And so it's at the core of pretty much all intelligent control. So now let me switch to the actual technology drivers. So the number one hands down winner in terms of being of a technology driver is computing. The computing capability, size, and cost has dropped exponentially for about the last 50 years. So shown here is what described as the famous Moore's law. Gordon Moore of Intel said in 1965 that he would expect that the feature size and the number of the line widths would double every year. And so this is exponential growth, and this has held up pretty much for 52 years or so. It is tailing off as we start to get to really small line widths, but it's held up pretty remarkably. And this is the exponential growth that is at the heart of the revolution. In fact, it's such a powerful concept that Moore's law has become sort of the paradigm for talking about the progress, the exponential progress of technology. So what is it about the IC revolution that's so significant? And that is really the line widths. If you look at the feature size and the size of devices, starting with vacuum tubes in the 1900s to the transistor in 1947, the IC chip, you can see that the feature sizes have just become incredibly small. Right now, it's in 2020, the line widths of integrated circuits are about 100 times smaller than a bacterium. So this is the sort of, this is really the story of the revolution of the 20th century and going forward. One other technology driver I wanted to mention is the whole area of microelectromechanical systems, or MEMS for short. This uses these MEMS devices, sensors mostly, use the same technology as integrated circuit chips. And the nice thing about that is by using the same process, you can have your sensor and processing on the same chip and drive down the cost, so that these MEMS chips, sensors can be installed on anything for pennies. So your cell phone typically today has 8 or 9 or 10 sensors, which are mostly MEMS sensors. So let's get into a little bit on the sensing side, get into a little bit more detail. So sensors are the interface between the physical and digital worlds. They convert a physical parameter into an electrical signal, which can then be converted to a digital representation in the computer. So all of the physical parameters like weight, distance, time, temperature, and so on are sensed by a multitude of sensors in electron, and then converted to an electrical signal, which is then used by the downstream electronic hardware or computer. There are essentially an infinite number of sensor technologies. Essentially, these sensors can be embedded into almost every imaginable product that exists today, all the way from appliances to robots. So let me focus on one specific sensing modality, and that's vision. Vision is by far the most powerful sensing modality that exists today, both in the biological world and in the artificial world. Typically, when the human eye is responsive for a very tiny slice of the electromagnetic spectrum, as shown here. And this is the artificial equivalent of this is called the CCD sensor. Most of the cameras that we use in our cell phones or on robots or automated driving vehicles are CCDs. And they work by taking the photons, converting the photons into electrons. That is the photoelectric effect. And those values are essentially stored in a matrix of numbers. So shown here is a set of pixels from 0 to 255. Numbers can be anything. But once you have it digitized and you get it into a computer, you can essentially do any sort of processing that you're interested in. So again, to look at our biological analogy, the human eye has about 150 million sensors on it. They're called rods and cones. And these sensors on the back of our retinas perform a whole bunch of pre-processing functions. And then those are sent to the brain. And the amazing thing is the brain uses about 30% of its neurons just for visual processing. And we do amazing things. We can process color, detect motion, shape, et cetera, et cetera. In the artificial world, of course, it's much more limited compared to the human vision. Once we get 2D image, we typically send it through some image processing hardware. And shown here is an example of a robot that's performing something called a bin picking task. And so the vision system looks at the bins, it figures out what is where, and then it guides the robot hand to pick the right part. And this is a fairly common application. I'd like to switch to touch sensing, which is probably the second most powerful sensor in our human body. When you think about it, most of our body is a touch sensor. We have skin all over our bodies. And this figure shows as a cutaway or a cross section of a portion of our skin. And one of the things that I want to point out is the diversity of the types of sensing nodes in the skin. we don't just sense touch, but we sense vibration, force, position, motion, texture, a whole bunch of things. And so this has been now become a very powerful and active area of research. People are building touch-sensitive skins for robotic hands. So when you think about a prosthetic hand, a person can get the same sort of sensing feeling that we have in our fingers by embedding tactile sensors into the hands, into the fingers of the glove or the prosthetic hand. The next concept I wanted to mention is that of sensor fusion. Sensor fusion is the use of multiple sensors to accomplish a task. In biology, we use it all the time. We have 5 senses in the human body. And so, for example, if you're sitting in your car and your engine's on fire, you don't have to go and open the hood and look, because you can feel it, you can hear it, you can feel the heat coming through the dashboard. So the brain has a mental model of, you know, what it means for all these things to be happening, and says, car's on fire, I better get out of here. So this is a very powerful concept that we use in autonomous vehicles, for example, or in any autonomous system. So in the smart car, we have ultrasound sensors, radar sensors, video cameras, LiDAR, which I'll talk about next. And these are all fused to produce a unified view of the world that's used by the car to guide itself. So now I'd like to move on to computing. So once we have the sensor data, what do we actually do with it? And here I'd like to divide my talk into 3 areas: architectures, embedded systems, and algorithms. Computing is a vast field in of itself, so I'm just going to focus on some very specific pieces of it that relate to intelligent systems. So we can think about architectures at a hierarchical level. So in this case, shown here is 3 levels. We have the sensors and controllers at the lowest level. Then we have something called edge computing, which is performing the processing as close to the physical asset as possible. And this is something that is becoming more and more popular these days because of the power of our sensor, our computer hardware. And then, of course, there's processing up in the cloud. And these 3 levels, because of the power of computing, a lot of the functions that used to be in the cloud, real-time functions, that is, are migrating downwards towards the edge and into the devices themselves. Here's an example of multiple robots working together in an automation line. Here, the computing is both horizontal and vertical, so distributed both hierarchically and horizontally, and multiple agents communicating with each other or via the cloud. We also have a lot of distributed functionality nowadays. So for example, when you look at Siri or any voice recognition system, when you issue a voice command, that data is transmitted over the internet to a backend or a middle tier where the speech recognition happens, and then the data tier brings up the information that you requested and sends it all back. And this happens in less than fractions of a second. And so when you think about the kind of real-time behavior over such a vast distance, it's quite amazing how fast this has been progressing. So then the ultimate connected system, of course, is the Internet of Things. And I think most people are familiar with the term. So for example, the estimate is by this year, we'll have about 50 billion devices connected over the internet. And that's more than 5 times the human population when you think about it. Let me now get to the nuts and bolts of an intelligent system. So the first fundamental step going from the physical to the digital world is something called analog to digital conversion. And as I mentioned before, that what that means is taking continuous signals and digitizing them into numerical values. And typically this is done with just integrated circuit chips these days. So once we have this data in the computer, what do we do with it? And of course, there are thousands of algorithms that are possible. I'm going to focus on the AI algorithms since we're talking about intelligent systems. So historically, the first sort of AI algorithm to be used is what we call expert systems. And essentially an expert system emulates the decision-making ability of a human expert. So the way it works is the knowledge from the expert, whatever it is, whether it's science or math or art, is stored in a knowledge base. And then when the non-expert user asks a question, the query goes to something called an inference engine, which then taps into the knowledge base and pulls back the information that is in there. And some of the earliest implementations of AI were expert systems. So this is an example of an expert system, which is a forward chaining algorithm, shows a bunch of if-then-else rules. And the application here is a simple temperature control system. So you're reasoning forward from data to conclusions. The other example of these expert systems is fuzzy logic control. Fuzzy logic is an interesting, very interesting real-world example of expert systems. I don't have too much time to get into the details, but if you have some time, you can Google some of these examples. Shown here is an example of an expert system that's being used, that is being used to control a subway system in the city of Sendai in Japan. And just by using linguistic rules, just like a human being would think about controlling something, they've been able to produce very precise control of the subway system, subway cars, that makes the ride extremely comfortable for the passenger. The other interesting thing about fuzzy control, fuzzy logic, is that it can be applied to simple devices. This is a system that I helped build in GE in 1995, which uses something called a turbidity sensor or a soil sensor, which senses the soil level in the water, and it uses it to control the number of cycles and the amount of water used. And this saved about 30% of the energy in the wash. So it doesn't have to be very complex systems either. Okay, so now I'm going to switch to artificial neural nets, which is the big branch of AI. And this is an area that is now probably, we might say, the hottest area of artificial intelligence. And the basic concept here is, of course, as the figure shows, we are inspired by the neurons in the human brain. And that's the basis of artificial neural nets. So let's take a look at how the biological neuron works. So if you look at the figure on the top left, impulses, electrical impulses, are carried towards the cell body over these structures called dendrites. And those are then transmitted to the nucleus of the neuron, which then performs some sort of computing or thresholding operation on it and sends a signal down the cell body called an axon, which then goes to other terminals, axon terminals, which then go to dendrites. And there are about 100 billion of these neurons in our brain, and each of them connects to about 7,000 additional neurons. So you can just imagine the astronomical number of connections. The artificial neuron is based on this model. So there's the algorithm that's used is very simple. It just takes a weighted sum of the inputs and goes through a transfer function of some sort and produces an output. So these neurons are then arranged in layers, all the way from the so-called input layer, where we present the data to the artificial neural net. The inner layers then perform processing functions of various sorts on the input data, and then they produce outputs, which are then sent via the output layer. And that's the useful data. that's sent to whatever it is, the human or computer control algorithm. So the big change here is that all the stuff that used to happen in software is now happening in hardware. These chips, these custom neural network chips called hardware accelerators are now becoming very common. Shown here is a chip used in the Tesla self-driving car that does all this in hardware. The problem, of course, there's no free lunch, is that artificial neural nets are black boxes that produce outputs from training data, and it's very hard to say what's going on inside. And so one of the challenges that's facing researchers is trying to figure out how to explain to ourselves what it's doing. A big development further to traditional artificial neural nets is this whole area called deep neural nets. The big change in deep neural nets is that we have many, many layers, many more layers of processing than with traditional neural nets. And the way it works is when you're presented with an image, each layer learns a slightly more abstract representation. So the first layer may learn about edges in the scene. The second layer starts to look at curved shapes. The third layer looks at facial features like a nose or an ear. And the fourth layer or the 10th layer recognizes the entire object. And so the increased layer count allows a much more powerful pattern recognition capability. So now let's move on to the third piece, which is actuation. So once you sensed and you've done a control algorithm or issued a control action, something needs to actually make a change in the physical world. So you can think about actuators as being the inverse of sensors. So we go from the digital world to the analog world. So most actuators, whether they're motors or speakers or LEDs or RF transmitters, they need a physical analog electrical signal to drive them. So that is the third process in the critical process called digital to analog conversion. So as you recall, everything that's happening in the computer is in the zeros and ones and in the numeric domain. And we have to convert this into the analog domain. And this is accomplished by something called a digital to analog converter. So a D2A converter is primarily all chip-based these days, like A to D converters are. And the D2A converter takes the digital signal and converts it into a continuous analog signal, which can then be used to drive the actuators. So there are many, many different kinds of actuators, as you can imagine, almost as many as sensors. We have robotic grippers. We have actuators in control surfaces. We have actuators in the process industry to control flow. So there's just a vast range of actuators that are out there doing multiple things. So one of the things I just wanted to mention to you is, show you is some very interesting work going on in the robotics field called soft actuation. And this actually tries to mimic the actuators in our human body. We don't have rigid actuators in the hand. They're flexible, compliant. And this inspired by that, it's developed a very interesting concept. So I'm going to play this YouTube for a couple of minutes.
Soft robot, by definition, is a robot made of things that are not rigid or not hard. We make robotic actuators out of rubber materials. No sensors, no tendons, no pulleys, no rigid joints. If you think about if you were going to build a robotic octopus, what would it look like? That was the inspiration for our technology.
Can you break down the technology on a really basic level as far as the inflation and how it actually works?
Great. So it basically, we take elastomeric material, so rubber, build a number of fluidic channels into it, layer it with composites, so other materials of other stiffness. And then by controlling the pressurization, the rate of pressurization, you get bending or extension or actuating. And so if you think about inflating a balloon, it's hourly, with a soft robotic actuator, because you've built these layered composites and you've channeled the air in a certain way, you can get this gripping action instead of just an inflation, you get actuation.
And why is this better than a hard robotic hand?
Well, the best part is if you think about a traditional robot hand and you think about picking something up, it has to know exactly how to position. So it has to know the exact location of the object. It has to calculate its path. So there's a lot of numerical computation. And then there's sensors on those fingers. So it has to grasp that just enough, but not too much. So a lot of processing can be very slow, very tedious to solve this. What we've done is we've said, if you have a hand like a human hand, but it's made of rubber, it can just grab anything. And so that's what we do is we use very simple vision systems. We do very little grasp planning, usually just aligning on the long axis to orient something in a package, and you just grab it. And one of the questions we always get asked is, how does the robot know that you've changed the objects? It doesn't know, and it doesn't need to know. Is all of the material science and the hand and the actuators allow it to conform to any object.
So it's a relatively new technology?
It is. It's been in the academic lab for some time. We actually spun out of George Whiteside's lab at Harvard. He started this work in 2008, 2009 under a DARPA contract. We started looking at it in 2012, and in 2013, we decided it was mature enough to really bring out, put into an entity with a focus on commercialization.
So it is quite fascinating how this technology, instead of making things complex, it actually can simplify and at the same time do more sometimes. You, of course, cannot use this for high precision machining applications, as you can imagine, but for a vast majority of tasks in the factory, a soft robotic hand like this can do a lot more than a very expensive, rigid, precise hand. The next example I'd like to show in the field of actuators is probably the state of the art in terms of prosthetics. It's some work being done at MIT by this person called Hugh Herr. Hugh Herr used to be an expert mountain climber who lost both his legs in an accident, and he then decided to dedicate the rest of his life to building much more advanced prosthetics. There is a wonderful TED talk that I would highly recommend that you look at if you just Google Hugh Herr, MIT Media Lab. It's really inspiring. I'm going to play just a 2-minute segment of it, and just to give you a feel for the kind of technology that underlies this. So I'm going to fast forward to just oops. Sorry. Trying to get to the, doesn't seem to want to let me go forward. Let me try it one more time. Okay, so all right, yep, that's better.
It's human walking. It significantly reduces metabolic cost. It's so profound in its augmentation that when a normal, healthy person wears the device for 40 minutes and then takes it off, their own biological legs feel ridiculously heavy and awkward. We're beginning the age in which machines attached to our bodies will make us stronger and faster and more efficient. Moving on to electrical interface, how do my bionic limbs communicate with my nervous system? Across my residual limb are electrodes that measure the electrical pulse of my muscles that's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desires. This diagram shows fundamentally how the bionic limb is controlled. So we model the missing biological limb, and we've discovered what reflexes occurred, how the reflexes of the spinal cord are controlling the muscles. And that capability is embedded in the chips of the bionic limb. What we've done then is we modulate the sensitivity of the reflex, the modeled spinal reflex, with the neural signal. So when I relax my muscles in my residual limb, I get very power. But the more I fire my muscles, the more torque I get. And I can even run And that was the first demonstration of a running gait under neural command. Feels great. We want to go a step further. We want to actually close the loop between the human and the bionic external limb. We're doing experiments where we're growing nerves, transected nerves, through channels or microarrays. On the other side of the channel, the nerve attaches to cells, skin cells and muscle cells. In the channels of motor channels, we can sense how the person wishes to move. That can be sent out wirelessly to the bionic limb. And then sensors on the bionic limb can be converted to stimulations in adjacent channels, sensory channels. So when this is fully developed and for human use, persons like myself will not only have synthetic limbs that move like flesh and bone, but actually feel like flesh and bone.
So yeah, it's pretty amazing what's going on there. So I'd like to get to the second last phase of my talk here, talk a little bit about system complexity and risk management, because these systems are becoming so complex. We need to really spend a lot of time trying to understand how they work and the risk. So how do complex systems behave? Because of the complexity, what is happening is that we can only think about these things in probabilistic terms, even though they're deterministic. We had to think about failure rates and things in a probabilistic domain. The dynamic systems, there are just too many latent defects and failure modes to be able to fully test. So what ends up happening is we're just hoping versus knowing how they will work. So how we deal with this is to start thinking about assigning failure rates. So there's a very nice paper here that you might be interested in looking at called How Complex Systems Fail by this person at University of Chicago, which talks about this in much more detail. So basic point is that complex systems are just intrinsically hazardous and we can't eliminate risk. So there are some stunning and tragic examples of overconfidence in these systems. This is a autopilot self-driving car crash, Tesla car in 2018. The autopilot was engaged when the car crashed. And when they looked at the log, it shows that the driver was repeatedly warned about the taking his hands off the wheel and distracted driving, but didn't take any action until it was too late. So this is an example of a false sense of confidence. There are many more examples. There was an Uber self-driving car that killed a pedestrian in 2018, and this was the first example of a self-driving car killing somebody. Again, it was the example of a distracted driver. And it's not so much the fault of the driver, it's just that the complexity of the system has become so huge. For example, a new model car has about 100 million lines of software in it. A 1981 GM car, for example, by contrast, had just 50,000 lines of code. So it's just things are getting much more complicated. There's another example, famous example, unfortunately, is I think all of you have heard about the Boeing 737 MAX crashes recently. This is not so much an example of system complexity, but just poor design and training and poor human-machine interface. Without getting into too much detail, the basic problem was that the aircraft has two angle of attack sensors, which tells the system what the elevation of the pitch of the nose is, was automated. And so what happens is when the sensor tells you that you've got too much of a pitch, the control system tries to move the plane back down using the horizontal stabilizers, and that's fine. The problem is that there are two sensors, and typically in previous designs, you would have the control system look at both sensors, and if they disagreed, then it would allow the pilot to take over and make a decision. In this case, what Boeing did was just use one sensor to try and reduce cost. And it so happened in both these cases that that sensor was had an error. It gave a wrong reading, and it said that the aircraft was pitching when it actually wasn't. And so the MCAS, the automated system, pulled the nose down. And then the pilot tried to switch the system off and pull the nose back up, but then the system would switch back on in a few seconds. So there was this back and forth fighting between the pilot and the automated control system, and there was not enough to resolve that, and the planes crashed. So what do we do about this? And what we used to do, and what we do always, is that we have something called redundancy. So in this case, there would be two sensors at least. So if one sensor failed, you would know that the other one was working. The other way to handle failures and complexity is something called failure detection and accommodation. And the field of study here is, or practice is, prognostics and health monitoring. So typically what mission critical systems have is something called dual redundant or triple redundant flight control or flight sensors. And there's continuous health monitoring logic that's running in the controller that's looking to see what's failed and how to compensate for that. And there are also these offline systems called digital twins, which are running these models offline on the ground. There is, of course, a standard development process for systems. This, I don't have too much time, but if you're interested, this is the standard V curves that goes from validation to implementation. I mean, from design to implementation to validation. It's the traditional V curve, and it's a standard development process that people use to build systems. So I'd like to summarize now. So what I've tried to present is a common framework for intelligent systems, which is the See, Think, Do cycle. Of course, this is a very simplified view of the world. Our bodies, human bodies and natural systems have many, many more layers and complexities, and it's not hard and fast division between See, Think, Do as this cartoon shows. But it's a good, convenient paradigm to think about things. And the Internet of Things is, of course, just exploding the number of connections that you can make and between systems. So what are the technical challenges? One of the biggest problems with AI in general is that it can embed the biases of their creators. So the thing to remember is these training sets are created by human beings. And so essentially we're teaching these systems like you would teach your own child. And so whatever biases you have will end up in the system. There are black boxes, as I mentioned, so they become opaque. We have to be able to figure out how to understand them. There's a false sense of capability, as I showed in some of those examples, that we think the system is much smarter than it actually is. So we need better visibility and testing. And then, of course, cybersecurity is a huge issue, because the more connections we have, especially using the IoT, is just a huge expanded surrounding for hackers to hack into systems. So cybersecurity becomes a huge element. There are, like anything else, like any other advanced technology, there are benefits and risks. I've listed some of them. There are many benefits to intelligent systems: productivity, safety, efficiency, social benefits. You can equalize access for all people, environmental, growing more food, curing disease. But there's also a lot of pitfalls, unemployment, de-skilling, loss of oversight, alienation because of unemployment, increase in inequality, loss of privacy, authoritarianism, and ultimately control over our weapons. So like any other technology, we need to have this balancing act as we implement these systems. So with that, thank you for your attention, and I'd welcome you to contact me if you like, if you have any questions or just want to chat about anything. That's my email, and be glad to answer any questions.
Thank you, sir. We have a question session in the end of the entire session.
Okay, sounds good.
Yeah. Thank you, sir, for enlightening us on the topic. It was very informative. And we have 3 student teams to present their presentation now. Now I invite students from Rajalakshmi Institution to give a presentation on the topic, Prevent and Compensate for Complex System Failures, Different Approaches, and When to Use Them. Please unmute yourselves and present.
Sir, you can stop share your screen.
Yeah.
Thank you.
Thank you, sir. I now invite students from Rajalakshmi Institution. Please unmute yourselves and present. Sorry for interrupting, but then you'll have 13 minutes exactly to present and 2 minutes to discuss your questions with sir. So plan your time accordingly. Thank you.
Team Rajalakshmi can go ahead.
Very good evening to everybody, one and all present here. We at Team Rajalakshmi are going to present about how to prevent and compensate for complete system failures, different approaches, and when to use them. The team members of our institution are Adil Mohammed, myself, Vishal B from Electronics and Communication Engineering, Mohammed Rafat from the Department of Aeronautical Technology, and Jonath S of Biomedical Engineering. So I'm going to talk about additive manufacturing, otherwise known as 3D printing using artificial intelligence. 3D printing or additive manufacturing is the construction of a 3-dimensional object from a CAD model or a digital 3D model, where the products are built by adding or layering components on one another. So there are basically 3 stages in 3D printing: prefabrication, fabrication, and post-fabrication. So I will be focusing on prefabrication and post-fabrication and what AI has done to improve these. So in prefabrication, there are 2 things: design evaluation and generative design. In design evaluation, a particular software called Agile Metal Technology Software by Sculptio, they have given business case. A business case is a self-learning artificial intelligence software which analyzes the feasibility of your metal additive manufacturing project. It calculates risks and opportunities, and it also gives you any extra information in case you need a better material or technique which suits your needs. So next one is generative design, NetFab 2018 by Autodesk. It uses a cloud computing software to give you the possible permutations of your requirements. So suppose you can just input your requirements. What is the material you want? What is the existing weight? So this was used by Airbus, where they wanted to design a cabin, and they inputted their needs, and the software gave them the possible permutations, where they significantly saved CO2 and fuel. Next thing we are going to talk about is post-fabrication. In post-fabrication, we have defect detection and predictive maintenance. In defect detection, we have computer vision for defect detection by GE. Here, it helps us to find microscopic cracks or microscopic aberrations to improve cost and time, record layer to find defects. Even a small mistake can be a lead to a very big system failure. So even if it's not visible by the human eye, this computer vision can detect the failure of that part or material, thus improving its product quality, and maximize productivity. So second one is predictive maintenance. Predictive maintenance is that with the help of sensors, the machine predicts the remaining lifetime of the parts, and it also tells you when you have to replace it in case if it fails. Suppose the maintenance engineer is like, it's good, he doesn't know how, he can't tell when it'll the part will fail or something. So the machine can accurately analyze and tell you when the parts will be failed and so on. So the next thing,
Thank you, Adil. Welcome, everyone. So I shall be talking about and covering, and my topic will cover an overall outlook of manufacturing plant. If we look at the manufacturing industry, in our case, smartphone manufacturing and assembly unit, it will consist of 3 management protocols or systems. They are the employee management, the system management, and the environment management. So we shall look into these 3 forms of management along with the latest technologies deployed in a few of these industries. If we are going to draw a Venn diagram with the aforementioned management systems, we shall notice that the system and the employee management as the subcircles of the larger environment management. So in this slide, you will see that a smartphone is made up of several parts, and the smartphone that we use today is not as simple as it seems. A lot of technology and processes run beneath the colorful screen you see, and that's the battery, the framework, the modem, antennas, the interconnects, the memory, the camera, the microphone, and a huge load of sensors connected to the motherboard equivalent of a smartphone. So while manufacturing a mobile phone, one must be very careful in joining the pieces together. If one system stops working or malfunctions, it will create a ripple effect on the performance of the other components as well. So moving on to the next slide, you'll notice the first part of the presentation, which is the system management. And towards your left, you'll notice that the 3 parts of the system management would be the pre-evaluation, monitoring, and control. Monitoring being the management of the system during the fabrication or the assembly part, and control will be after the result has been obtained. And in the level of system management can be either in the case of component level testing or in the case of system level testing. So whenever a component is manufactured, it will be subjected to several test cases in particular environment, and the same behavior when it's going to be attached to a component B, C, D in a system. If the behavior of the component doesn't match, it would be a defect. So that would be a monitoring system. There must be a monitoring system to know if the particular component is going to be working properly as a standalone unit as well as in the system. So moving on to the next slide, we'll notice the large-scale sensor networks which can be connected to the internet. There will be a lot of short forms here. It's very simple actually. ISN is the intelligent sensor networks, which are going the sensors and the actuators, which form the first level of interaction between the computer and the human, followed by the the PLC, the DCS, the distributed control systems, the SCADA and the DAS, as well as after that, if you move upwards, you can notice the MES, which is a form of a manufacturing operations management, and also the ERP, which is a enterprise resource planning. So towards the left and the right, you can notice that there is a flow diagram which moves from the the level 4 to the level 1, and also from towards the right, you can notice the data being flown from the sensors to the ERP, and the level 0 can be compared to the physical layer of a computer network where the transmission of data occurs. And in the next slide, you'll notice the second part of the presentation, which will be the employee management, wherein the activity of an employee is being monitored continuously using the data, which is a camera in the sense. You can notice a GIF file here that has been attached in the presentation towards your right. The eye has been tracked continuously so that we can notice if the person is going to be focusing on that particular segment while assembling, or is he going to, his eyes are going to wander somewhere else. And moving on, the last part of this presentation will sum up the system and the employee management, which is the environment management. So sensors form, as Sir told, sensors form the first line of action between the humans and the computer. So there will be several sensors, but in the industry, the sensors cannot be integrated with any form of electromagnetic form of communication, since the in industries the EMI is the interference is plays a major role. So we'll be creating ad hoc networks whenever and wherever required, and the transmission through that would be very feasible, and it's an upcoming technology as well. So that's my part of the presentation. Over to you.
Thank you, Vishal. So coming back from here, we will see what will the intelligent systems which can prevent and compensate in the failure of the aviation industry. So let me proceed with a small case study with present and future aviation, which can be implemented in the next 10 to 15 years. So the case study is the passengers air travel. The step 1 is search and book tickets in the concerned websites. And the second step is successful flying to the destination, which in the other term we may say flight operation systems. So these two systems are completely depending upon the passengers' demand to travel. So third one is the post-flight process, which is nothing but the MRO, maintenance, repair, and overhaul operations. This step is completely depending upon the airline which operates the aircraft in that demand routes from the passengers. So in step 1, we have several several applications with respect to the AI is dynamic pricing, pricing optimization, flight delay prediction, flight route optimization, etc. So coming to the step 2, successful flight to the destination is the flight operating system. So here you look the mission profile of the commercial flight system. So what is happening right now in the flight operation is, in today's date, what level of automation we have in the flying of an aircraft are very even automatic right now. So current autopilot, which is nothing but a computer which operates aircraft according to the pilot input only in cruise segments of the flight by maintaining a particular altitude, heading, speed, etc. As of date, no airplane has an autopilot which can take it off as their own. So whenever we are in airplane, we have to remember that pilots have the control in their hands and doing the rotation and flying the aircraft manually. This is still now. But Airbus recently changed this entire concept. Airbus, as of now, on its A350 1000 extra wide body variant, tested autonomous taxi, autonomous takeoff, and autonomous landing system. For these operations, Airbus put up some image sensors in the front of the aircraft, basically giving the aircraft its own eyes. And the aircraft can recognize the runway center line and automatically maintain it. The autopilot will sense the runway and runway center line with respect to the speed and automatically makes the aircraft nose up and gets the aircraft airborne, which when it reaches the rotation speed. Similarly, the same algorithm can be used for taxiing and landing. All of this doesn't mean pilots are not required in the future, but this automation is mainly for two reasons. One is to reduce the pilot's fatigue and to improve the main safety of the flights. So the more the automation, the safe operation becomes within the pilot's control. So the next one is the post-flight process. So some of the worst aircraft disasters have happened due to the faulty or overlooked maintenance. So now the implementation with AI, aircraft companies can predict potential maintenance failure on aircraft before any mishaps occur. So first one is the smart maintenance. Predictive analytics by AI through maintenance data. AI can interpret and organize data from sensors and send the data in a report on potential failures in real time and arranges proper timelines for repairs. Second one is the augmented reality with Internet of Things. With the latest advancements with this technology in testing stage, now the AR glasses enable to see hands-free 3D diagrams rather than viewing 2D diagrams. According to developers, this technology in the testing stage itself already shows a 90% improvement in first-time fixes and 30% in the reduction in repair time. Third one is the flight health check and maintenance. Recently, the Rolls-Royce, which is the premium manufacturer of aircraft engines, has partnered with Azure IoT Solutions with the help of AI to accumulate data with sensors being used in aircraft engines to check the health of the engines in real time and find the best predictive maintenance. These are the digitized troubleshooting methods in aircraft maintenance under MRO operations. So, coming to the conclusion part, we have to treat the AI as a technology, not as an intelligence. By making this statement true, I would like to share a quote by the famous theoretical physicist and cosmologist Dr. Stephen Hawking. Success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last, unless we learn how to avoid the risks. So by considering the Stephen Hawking statement, what I believe in the Airbus 82L program, the Airbus clearly states that systems can managing the aircraft while the pilots remain at the heart of the operations decisions. So which means at last, whatever the technology comes, the last and final decision should be taken by the human with respect to the mankind. If we fail this is what happens like in the MCAS system failed in the Boeing 737 MAX variant, which is likely said to be failure of an AI, which cost hundreds of lives in the last two accidents. Thank you.
So thanks, Rafat. I'll be talking about how to prevent and compensate for failures in biomedical engineering. What you see now is a Da Vinci robotic surgery unit, which allows the doctor to perform a surgery from a remote place. In the next two slides, we'll be talking about some failures. So in the next slide, you can see some major failures. First is the system error. In case of any software or hardware malfunction, the system raises an error code and the device itself tries to solve it. If it is not possible, it will warn the doctor and stop the surgery and suggest him to go for a traditional way of procedure. And there are possibilities for the instrument to get broken and fall into the patient's body cavity. In that case, it turns into a diagnostic mode and allow the operator to remove the part carefully, preventing any further complications. And there are also possibilities for electrical arcing and tears in the tip cover, which is used for preventing the instruments from corrosion. So to prevent this problem, they have modified the mechanical part of it, which does not allow the instrument to get through the cannulation device. And in the next slide...
Sorry for interrupting, team. You just have 2 minutes more. You can continue.
Sure. Thank you. So in this slide, we'll be talking about three common problems. First is an unintended instrument movement. in certain cases, the surgeon will try to move in a specific way in a controlled manner, but in the robotic arm side, it will have an excessive movement. So to control that, we'll be having a disturbance or a tremor reduction algorithm, which just extracts only the essential part of the movements and progress it to the robotic arm. This will greatly reduce the complications. And video problems will occur in case of display failures or while moving the surgery unit from from one place to another. And till now, there is no intelligence to solve the display errors on its own. We have to go for a service. And the final problem is a problem with electrosurgical unit. Because in case of surgeries using diathermy and coagulation using heat, we go for a short circuit development, a safety short circuit development, which produces the necessary heat for cutting. So to prevent any sort of electrical arkings in electrosurgical unit, the instruments itself have an inbuilt data logging device, which just holds how much time the instrument has been used, and if it is being operated in excess of the prescribed expiration time. So in cases like overusage of the instrument, the robotic arm does not allow the instrument to be operated. That particular robotic arm will be unfunctional. So these are certain things which is available in DaVinci. So as said by Rafat, in case of aviation, it is always necessary for human intervention, though a machine is taking over a particular function, to prevent any sort of complication and to take into consideration the patient's safety. So thank you. That's my presentation.
Thank you, team. Your time is up.
Okay.
Thank you for the informative and innovative session. Now, I request Team Savita to present their vision on deep learning, biggest application and limitation, how it differs from traditional artificial neural network technology. Team, you have 15 minutes and you can split accordingly. You can take over.
Am I audible?
Yes, you are.
Yes.
Yes, you're audible.
So, a very warm welcome to one and all present here. This is Samreen Fatima. My friends and me are here to make you expand your knowledge by familiarizing you with an interesting topic, deep learning, its biggest applications and limitations. So, during my speech this evening, I'll be providing you with some of the backgrounds on deep learning and letting you know why it is so important to know it. Next slide. So, DL is a part of our daily life. We encounter deep learning almost everywhere on the social media platforms. That makes it more interesting. Is the screen presented?
No, Savita team, your screen is
Sandhya.
not present.
Sandhya, please present your screen. Yeah. So these are the contents we would be throwing light upon. By the end of the presentation, you'll be able to know what deep learning is, its techniques, applications, and how helpful it will be in future. To understand deep learning, you must first know what AI and ML really are. So now my friend Samatmika will carry on with the session and explain the same.
So it is very common that people are confused with the terms AI, ML, and DL. So let me make it easy for you by giving an example. Consider a company which has a system that is able to give jobs to people that enter the company. So in what way does AI, ML, and DL differ in this? The system as a whole is called AI. So what is the part of ML here? So in order to determine the position for a particular person, we need their experience, we need their salary, we need their age. So by finding comparisons and by
getting the data, we just can find out whether they get to be in a higher position or a lower position using ML. So what is DL? So consider a human being is doing this job. So think as a human. So in case of DL, you'll have more number of features like thinking how they communicate. So even based on the communication, we can give them the post. So in this way, we can differentiate these things. Also, AI is the main part. ML is a subset of AI, and also deep learning is a subset of machine learning. Now moving on to the next slide. So what made AI, ML, and DL so popular all of a sudden? It is because of the huge amount of data that we have with us. So as you can see, as of 2020, we have 44 zettabytes of data. Consider how much huge it is. So with this much amount of data, we can do a lot of things. So now let me give an example in determining how ML and DL solves a problem. Consider a mango. You need to find out whether it is a mango or not. In case of ML, you need to feed in the features like color, shape, and size. And this is done by a domain expert who will give these features. And based on these features and the correlations between them, the machine will find out it is a mango. So in what way DL differs? In case of DL, you will first find the edge. It is like the working of a human brain. You will first find out the edge, and then the overall rough shape of the fruit, and then the color, and then you'll find out that it is a mango. And you do this with what you call artificial neural network, about which we'll see in the future slides. Moving on to the next slide. In the recent years, DL has been surpassing ML in a lot of ways. So why is it happening? So as we can see, who is the most intelligent in the world? It is obviously the humans. So if a machine can work or mimic human behavior, it is obviously going to be surpassing every other thing. So consider an example here, YOLO object detector. YOLO is a famous deep learning algorithm. So with this YOLO object detector, we can detect objects like car, bike, bicycle, or even a human being on the road. So the same can be done with the ML. So why is DL surpassing it? So in case of ML, you can do the same. As you can see in the below diagram, it is going to be a bit clumsy there. So with this, you can understand how complex it is going to be to do the same with a machine learning algorithm. And in the machine learning algorithm, they have used SVM classification, support vector machine, which is a famous machine learning classification algorithm. So with this, we can do the same thing, but it is going to be complex. And also, there is a quote by Andrew Ng who says, data is to a ML model as fuel is to a rocket. So the more and more data that you give to a DL model, the more better will be the performance of the DL model. So without further ado, I'll give it back to Samreen to continue.
Okay. So rather than giving you an actual definition of what deep learning is, and to make things simpler, I thought of starting off with some stimulating real-time examples. So first, I would like to explain about language identification. Let me tell you how it works. A machine will make a decision that someone is speaking English and make a distinction based on the dialect, and all the process is done without any human intervention, both based on deep learning. Take a moment to digest this. Researchers have developed an AI system that helps robots copy human demonstrative actions. Deep learning helps robots execute tasks like human brain based on their past experiences, image analysis, and caption generation. It is one of the greatest feats of deep learning, and it has the ability to identify images and generate captions for them. Now, Snapchat also uses deep learning, but I personally like using Instagram during my free time, watching videos, reels, food recipes, reading quotes from it, and my list goes on. Okay, next slide. Now that you have an idea about the basics, let's get to know the actual definition of deep learning. So what exactly is deep learning? It is a technique to help machines think and work like humans, and it can perform any task without the help of human intervention and tries to replicate the human brain structure. It no longer uses traditional algorithms but uses several neural networks. Okay, so now, have you ever wondered how Amazon comes up with the idea for what they must buy next, or Netflix comes up with the suggestion of what you should watch next? Yeah, it's deep learning. And now you might be thinking, how is it so extraordinary in performing its task? It is because of the ANNs, that is, the artificial neural network. So now my friend Shruti will illustrate to you about the same in the next slide.
Hello everyone. What actually is artificial neural network? The technical definition goes like this. An artificial neural network is an attempt to simulate the network of neurons that make up a human brain so that the computer will be able to learn things and make decisions in a human-like manner. Oh, that sounds too complicated. Explain to me as if I'm a 5-year-old kid. If this is your reaction, here, I have a relatable explanation. So just imagine a human brain, which is completely empty. When you place two objects, in this case a broccoli and a candy, in front of it, it initially assumes that they both would be nice and gives each of them 100 points. So these points are technically called the weights of the input. So then, the brain tastes both the food and then decides that broccoli isn't that good and gives 1 point, and lollipop was more tasty and stands stable in its 100 point. So basically, only after we insist on experimenting with categories, we get the desired output. This is in regarding to a human brain. But when this happens artificially with some algorithms, then it is called the artificial neural network. Let's now jump into an actual working of ANN in the next slide. So, how many times you've just seen someone and thought you've already seen them before? It's basically because of the neurons in your brain. When you see something, the neuron spikes back to billions and zillions of memory, which is already registered, and insists you that particular thought. So the exact same thing happens in ANN. We give some inputs. The inputs can be in any format: images, data files, audio files, etc. And each of them have a particular weight. And what the neuron does is it sums up all these inputs and generates the output. To get a better clarity on this, let's just look at an example in the next slide. Imagine an industry producing fruit juices. The raw materials for the production are a mixture of fruits. So consider they are inventing a machine to classify the fruits accordingly. The mixture of fruits goes through the conveyor belt and enters into multiple hidden layers where they are classified based on their color, shape, texture, and so on. So as you can see, the apples, oranges, mangoes, and raspberries have unique identity features, and the machine uses these features to classify. And at the end, you get the separated or classified collection of fruits. Once this is done, the workers can give labels to the output and then use backpropagation to correct any mistakes that have been made. After a while, the machine can carry out its own classification task without needing humans to help every time. So this is regarding the industry when the same thing is happening or when same thing is processed through algorithms to a computer network. The carried out task is briefly known as the artificial neural network. That was my time. Abhinaya will now take over.
Hello everyone. Now we can see the difference of DL and ANN. Artificial neural networks, usually called as simple neural networks, that is nothing but a computing system inspired by biological neural networks. ANN is based on a collection of connected units or nodes. Importantly, deep learning is a subset or a subfield of ML, and neural networks makes the backbone of DL algorithm. The following diagram shows the difference of neural network and deep neural network. All these individual nodes are neurons and they have some structures and working. It is categorized into 3 different layers. Input layer, neurons in the hidden layer do the processing, and the output layer. As the diagram shows, if there are 1 or 2 hidden layers, it is called as neural network. If there are more than 3 hidden layers in a network called as deep neural network. All deep learning is a neural network, but not vice versa. Deep learning is a subset of neural network, and it is an approach to AI that enables computer systems to improve with their experience and data. Let's see the graphical representation. As the graph explains, the performance of DL is increases when it has a high amount of data. According to the input and the amount of data we are provided, we can see the increased and decreased level performance of DL and ANN. When there is a large amount of data, the neurons may give the output accurately. Next, ANN is the functional unit of deep learning, where DL uses ANN, which mimic the behavior of human brain to solve some complex data-driven problems. Next, applications of deep learning will be continued by Vabhusha.
By knowing the process of deep learning and neural network, we would have known that this process may take hours or even months to be trained. because the amount of data is really huge. But I think time would be a reasonable trade-off when compared to its scope, because every field we come across in our day-to-day life has something with deep learning mechanism. Here, we will see some of the futuristic and primary applications. Self-driving cars. Though this is not implemented completely, the process of driverless cars or delivery system without human is fully enforced, and companies like Apple, Nissan are all working on this. This would be a great product in the future as it can prevent accidents. Visual recognition. When you click a picture, some phones automatically classifies them by recognizing the people, food, location, etc. From converting black and white to color images, restoring damaged images, identifying your face by connecting the spots in line, all these are product of deep learning. Next slide, please. Medical field. From medical imaging to analyzing genomes to discovering new drugs, the entire healthcare industry is in state of transformation, and GPU computing is the heart. It helps in accurate and speedy diagnosis of life-threatening diseases, which can save a lot of time and money. Fraud detection. In banking sector, fraud prevention and detection are done based on identifying the patterns in which the customer transaction takes place or identifying any anomalous behavior. While as a news sector, fraud news detection helps in finding any fake news and remove it from your feed and warn you of any possible privacy breaches.
Sorry for the interruption, but then you have only 2 more minutes left.
Yes, thank you. Now to discuss the limitations, I would like to hand it back to Abhinaya.
Next is about limitations. Deep learning has vast scope, but it too faces some limits. Yes, when we see that there are major three of it. While deep learning is most efficient way to deal with unstructured data, it requires very large amount of data in order to perform better than other techniques. For example, let's assume we always have to access necessary amount of data processing, and so this is not within the capability of every machine, and that brings us to our second limitation, that is nothing but computational power. Training an artificial neural network requires graphical processing unit, which have thousands of cores as compared to CPUs and GPUs. And moreover, they'll require expensive GPUs and hundreds of machines. This increases cost to the users. And finally, our third limitation is about training time. Deep neural networks take hours or even months to train. It is extremely expensive to train due to complex data models. The time increases with amount of data and number of layers in the network, so it will face some difficulties in training process. There is no standard theory to guide you in selecting right deep learning tools, as it requires knowledge of topology, training method, and other parameters. As a result, it is difficult to be adopted by less skilled people. Next, I would like someone to carry on the session.
Okay, the future of deep learning. Deep learning has vast majority of scope in the upcoming years. It can far surpass human intelligence and can deal with problems on its own. Deep learning in big data analysis. The concept of deep learning is to take large volumes of data to automatically identify patterns and extract features from complex data without any human involvement. The next one is the advanced cognitive system, which means it can intelligently and fluently interact with humans. It can also be used for fast coding with simple programming frameworks. Now have a look at the graph in the side. It shows how the demand for DL increases year by year in the future compared to the traditional.
Sorry for the interruption, but then your 15 minutes is done, team. If you have any questions to Vivek, sir, you can please post them.
Yeah, okay.
I request Vivek, sir, to kindly answer them, please, sir.
Sure. Rajalakshmi.
Hello, sir.
Sorry to interrupt. This is CNC here. Aren't we taking Q&A at the end? Can we just go with the flow of the team presentation?
Yes, sir.
Yeah.
Thank you for the knowledgeable presentation, team. We now have students from Sona College of Engineering to do a presentation on the topic, Computing Technologies Under Development in Anticipation of the End of Moore's Law. I request the students to please unmute yourselves and present.
Hi everyone, we are from Sona College of Technology. We are going to present our topic, Computing Technology under
under development in the anticipation of end of Moore's law. I'm Arun Kumar, and my teammates are Kavin Raj, Priyadashni, Meena, and Madhumita. I'm here to present you about Moore's law. First, we will see who's the Morse guy. Gordon E. Moore. He was the co-founder of Intel Corporation. Sorry. He was the co-founder of Intel Corporation. He states that every 18 months, the number of devices like transistor and DRAM in ICs are doubled. This law was proposed in 1965. In ICs, there are three main components. The first one is transistor. It is composed of N-type and P-type silicons. When we reduce the size of transistor, tunneling-induced leakage will happen. But we can stop this problem using thick dielectric insulator. The second one is DRAM. DRAM is dynamic random access memory. It is basic capacitor which means when charge is present, the binary value is 1, otherwise it is 0. And the third one is interconnects. It links the IC components using copper wire and it covers 70% of area. The underdeveloping technologies for interconnects are wireless interconnects and optical interconnects. Now my teammate Meena will present about limitation of Moore's law.
Hello everyone. Limitation of Moore's law. The problem of chip designers depends on transistor checking and the law of physics in particular, electron turning prevents the length of the gate. The part of transistor turns allowed the electrons on or off from being a smaller than 5 mm. And then we are going to see about fundamental limits of Moore's law. There are thermodynamic limits, illusion of quantum turning, thermal limits, quantum wavelength, particle upset, and conclusion. Thermodynamic limits. In thermodynamic limits, we need to irreversible change distributed states of memory cells. And second one is illusion of quantum turning. In this, there are two formulas. There are the probability of thermodynamic injections of electron over the barrier weight is GT is equal to exponential minus EBT by KBT by T. The second one is the probability of turning through the barrier is GQ is equal to exponential by 2A root of 2M by E by T. Third one is thermal limit. In thermal limit, we can allow the power to rise depends upon how much rise in temperature the chip can stand, typically up to 400 degree Kelvin, and how fast we can remove the heat from the chip. Fourth one is quantum wavelength. The quantum wavelength delta C is equal to H by MC. M is equal to N in 9 by 1 into N power 31. This is the only limit of the size of an electronic device. Fifth one is particle accept. Particle accept power consumption and speeds are limited fundamentally by the device. This is the reason for the clock speed to have a saturated at about 3 GHz. From all the above limits, we have the scaling limits in 30 to 40 years. This is not sure, but we can realize the fundamental locality activity compounds like semiconductor and semiconductor, which remain fantastic for a computing without power. Next slide. And we are going to see about why cannot this law hold forever. Moore's law states that the number of transistors on integrated circuit doubles every year, depending on which we can choose. It is held true for a very long time. And first, we can all have the point that all the matters, including semiconductor, is made up of atoms. This is the reason this law cannot hold this forever. And the end of Moore's law is handled by Madhumita.
Okay. The end of Moore's law. It's time to start planning for the end of Moore's law, and that it's worth pondering how it will end and not just when. That was said by Robert Colwell. He is the founder of the Director of Microsystem Technology Office at the Defense Advanced Research Points Agency. Semiconductors are in everything today, but if artificial intelligence is the future, silicon may not be the most energy efficient means for the compute power. Many designers are taking this equipped approach by looking at biology or the brain as a model of future networks. The best known example is DA or PA, called SYNAPS, that is, System of Neuromorphic Adaptive Plastic Scalable Electronics. That is developing a neuromorphic machine technology that scales to biological levels. The ultimate aim is to build an electronic microprocessor system that matches a brain in function, size, and power consumption. It could recreate to 10 billion neurons, 100 trillion synapses. It is same as the same electric heater. Next slide. Neuromorphic computing was originally conceived by Caltech professor Carver Mead. In his 1990 IEEE paper, he wrote that large-scale adaptive analog systems are more robust to component degradation. Deep learning algorithms are very powerful, but they rely on processor to calculate and simulate the electrical states. We have come up with electrode that's simple, expensive, and more efficient. As a result, it was easy to modify it for further study and applications in the future. So the types of technologies will be explained by my teammate Priyadashni.
By the end of Moore's law, what are all the technology that meets the Moore's law? Let's see those technology one by one in detail. Firstly, quantum computing. First of all, let's see what is quantum computing. The computer that performs quantum computation is known as quantum computers. The quantum computer is an area of computing focused on developing computer technology based on a principle of quantum theory. The basic unit of conventional computation is the bit. If the computer has more bit, then it performs more calculations. Within quantum computing, the conventional computation is qubit or quantum bit. The qubit or bit is different and it doubles computing power. For example, 10 qubit computer could do 2 power 10 calculation at once. 1000 qubit computer could perform over 1000 billion calculations simultaneously. Quantum computer can solve many problems at easy method. Next slide, please. And second technology is three-dimensional chips. We all know initially the guts of computer have always been two-dimensional. Flat computer chips sit on a flat motherboard. Nothing moves in three-dimensional. There is no ups and downs inside a computer chip. Finally, on 2019 December, three-dimensional chip was created at Stanford. The Intel INTC introduced its three-dimensional chip technology. Three-dimensional chip uses carbon nanotube to stack memory on top of the processor. That way, it's all compacted into one place. And they say it is 1,000 times faster than normal computer chip. Then everyone's question was how Intel will meet the Moore's law. Of course, the answer is chips stacked in 3D or far superior to one placed side by side. Not only can you fit multiple of transistors in a same footprint, you can also better to integrate all chip function. And it creates many more pathways for information to flow. Finally, we get the result of 3D chips in much more speed and power packed into small space. Eventually, three-dimensional chip could do 1,000 times faster than existing one. Next slide, please. And third technology is optical computing. An optical communication circuit is also known as photonic. The transistor, what if instead of using electron to do, you use a photon, that is the particle of light in transistor is called photonic transistor. In 2013, scientists at MIT created the first optical transistor which used a beam of light instead of flow of electrons. They were even able to send only one photon over the time, but it is primitive. Manufacture of photonic chip is made from the semiconductor with numerous holes in it, making it appears much like a honeycomb. Lights entering the chip becomes bounce around and get trapped by the holes. A small crystal called a quantum dot sits inside the area where the light's density is strongest. Photon can travel about 20 times faster than electron in a chip. That means the computer that are 20 times faster and speed. Next, the graphene nano ribbon and DNA computer will be handled by Kavinraj.
Graphene nanoribbon With each new generation of microchips, transistors are being placed closer and closer together. This can only go on so long before there is no more room to improve, or something revolutionary has to come along to change everything. One of the materials that might be the basis of that revolution is none other than graphene. Researchers at the University of California at Berkeley are hot on the trail of a form of so-called nanoribbon graphene that could increase the density of transistors on a computer chip by as much as 10,000 times. Graphene is a sheet of carbon, only one layer of atoms thick. Researchers have been working on producing high quality sheets of the material, but nanoribbons ask more of science that it can currently deliver. Transistors based on nanoribbons could also be packed very close together. A human hair is 10,000 times wider than Fischer's nanoribbons. Thus, a chip based on graphene nanoribbons could have a huge number of very fast transistors that dissipate heat more efficiently than metal. If the process is perfected and scaled up, graphene nanoribbons could allow all electronic circuits to be improved dramatically. Everything from CPUs to storage technology could get faster, and Moore's law might have a future after all. Next slide. DNA computer. The drop of pink solution in the pipette, which contains millions of DNA molecules, could store 10,000 gigabytes of data. Over the past few decades, it has become apparent that Moore's law has started to come apart. The 1965 observation, named after Gordon E. Murray, stated that the number of components on a chip seemed to double every year, but we are reaching the limit of silicon's storage capabilities. To keep pushing the boundaries of each computing technology, we will need to rethink the basic components of computers themselves. Current archival facilities, such as the Data Storage Center of Facebook, recently built in Oregon, occupy entire warehouses and they can store about an exabyte, that is 1 billion gigabytes of data at a maximum.
Sorry
That's
for
just a
interrupting, team.
fraction of.
Excuse me. Sorry for interrupting you, team. You have only 2 minutes more.
Thank you, ma'am. That's just a fraction of the entire internet, which is forecast to reach 16 zettabytes or 16,000 exabytes. SEAS is part of a team of researchers at the University of Washington that has developed a new method of encoding and reading information stored in synthetic DNA. They only encoded several megabytes of information. SEAS says that the process could be scaled up to hold much larger databases. If we compare flash to DNA in terms of density or the number of bits in a certain volume, DNA will be at least a billion times denser. You can put a exabyte in a cubic inch, which would be a few sugar cubes, says SEAS. So with this, we are closing our presentation. Thank you for all.
Thank you, Sona College of Technology, for a wonderful presentation. Now,
Thank you,
I
ma'am.
request Rajalakshmi institutions, if you have any questions, you can unmute yourself and talk.
Yeah, this is Dr. Yogesh. I have a question for Dr. Badami. Sir, in your, you can hear me, sir?
Yes, I can. Yeah.
Yeah. Sir, in your presentation, you showed one of the character of the movie Terminator. Now, my question is, how close are we with respect to technology to come out with a similar robot? And my one more second question is, if you can throw some light on digital twin, because whenever we do any searching, always GE are the front runner in this technology, sir. Thank you.
Yeah, sure. So on the first question, how far are we, how close are we to something like the Terminator? Fortunately, I think, in my opinion, we're a long ways off. Because the kind of generalized intelligence that we have, where we can work in unstructured domains with our vision systems, with our actuators, and the computing is just so far ahead of anything we have. All of these systems like deep learning that use, that are beating the world champions in chess or whatever, they're very narrow domain, very, very specialized. So the generalized humanoid or cyborg of sci-fi movies is a long ways off, in my opinion. To your second question about the digital twin, yeah, you're right. GE is using that data, that approach all over the place. It's being used both on the ground for gas turbines and for aircraft engines pretty widely. The basic concept, so how is a digital twin different from a model is a question that most people ask. And is it just a buzzword? To some extent, it is a buzzword, but it's a little more than that. Traditional models are, they have a physical model or a computational model of, electrical model or whatever. But digital twins actually have more than just those models. They actually have the history of the asset, how many times it's been serviced. So we know the remaining useful life, as one of your speakers pointed out. Those things are really crucial, especially in the area of prognostics and health monitoring. So yeah, to answer your question, digital twins are becoming very popular. Not just GE, but other manufacturers as well. I hope I answered your question.
Thank you, sir.
Team Savita, if you have any questions, you can unmute yourself and talk.
Hello, sir. I'm Rajalakshmi from Savita Engineering College.
Right.
We were inspired by all the awesome intelligent systems you spoke about, sir. And we have a few questions to ask you. First, we have 5 actually. First one is we have DL and AI now. How do you think it will grow to be? Like, what's next?
So I think deep learning definitely is going to be, seems like it's the future wave. Simply because of the amount of data we have. We just have gobs of data. And the hardware accelerators are really what's making it all possible. I think the future is really bright for deep learning, but the challenges are again, as I'd mentioned before, it's still a black box. And before we can hand off our, futures to a black box, we really need to understand what it's actually doing. How does it arrive at the answer it provided? So that's one thing. And as I'd also mentioned before, just in terms of embedding biases, it is a serious problem. If you teach it the wrong thing, it just does the wrong thing, and just as any human being. So there are actually groups at MIT and other places that are taking the whole concept of, how do you prevent bias in teaching from making the systems worse. So I think it's got a huge future, but it's just going to, I think there's a lot of societal hurdles to be crossed.
Yeah, this is Arun Dev. Sorry to interrupt. We do also have questions from the open forum that we have thrown open. So I request CNC to sort of go through those questions along with Dr. Vivek Badami and address whatever needs to be done. CNC, can you just stop in?
Yeah, thank you, Arun. I think the questions are pretty much common. There's a lot of overlapping questions. Just pick up one or two in view of the time constraint that we have, because we spent 2 hours plus, on this topic. Okay, so one question which is different from what has been asked is how dynamic voice recognition with less memory can be made. it looks like more a technical question. Vivek, would you like to take this question?
Yeah, I think I'm not an expert in voice recognition, but what's really happening is with all of this AI, these AI algorithms, is that hardware is now becoming so powerful that a lot of the algorithms that we used to have, things like voice recognition, the basic fundamental algorithms have been known for a very long time, since the 60s. But the thing is, actually implementing them has just taken along, needs a lot of compute power. So it's really with the hardware that's coming along and doing this in physical hardware, whether it's analog or digital, on chips, is going to make it much more powerful. One other thing is, if you've noticed with your Siri or any such thing, I've noticed is that it just seems to be learning in the background all the time. So it seems to have learned my accent. It seems to predict what I want to know. So all of this learning is happening in the background, just like your GPS systems. So the AI algorithms are constantly working and improving, even though it's not visible to us. So that's something that is really quite powerful, and also a little scary, because they seem to know a lot about me already, which is, something that we need to think about.
Right. Thanks for that answer, Vivek. I'll go on to the next question, which seems to be another unique one. What is the impact of sensors in this pandemic situation?
Oh, yeah. I mean, one area that I simply did not cover is the whole area of biochemical sensors. So I had listed, electrical and mechanical and other sensors, but biochemical sensors, things that sense proteins or other aspects of biology, biochemistry, is a huge, big field. So that's an area that I think now is going to come to the forefront with COVID. There are, when you think about it, all of our sensors, in the 5 sensors that we have, are really biochemical sensors. We are really just a biochemical factory inside. And so that's going to be a huge, big deal, because there are fundamental limitations to electrical sensors. So sensing biological properties directly, like temperature and salinity and pH and, even viruses, is going to be huge.
Okay. Thanks. There's one other question that I would like to take, that is to satiate the desires or the appetite of rice eaters in this forum. This question is relating to rice. What are the sensors available to assess the quality of rice? Can the particle sensor detect the dust particles in the rice, or it can be used for just monitoring?
Oh, so I don't know specifically what the sensors that relate to rice quality are, but you say dust, there are specifically sensors that detect dust levels. They do this electrostatically. We use them all the time in the gas turbines or aircraft engines, where you're trying to monitor how much dust is being ingested. I'm just guessing here, but that's something, if it's applicable to rice harvesting or quality control of rice or wheat, that's possibly a solution. But I'm not familiar with specific sensors that are being used in the agricultural field for things like rice monitoring.
Okay, I think that's good enough. In the interest of time for all of us, I would like to close the Q&A session. Nevertheless, I will forward all these questions to you, Vivek. Some of them are overlapping. You can group them in whichever way you like, and they provide an answer from out of your presentation and other knowledge. Thank you so much. Now we'll move on to So we'll move on to word of thanks, and I would like to keep it brief. So we have spent more than 2 hours on intelligent systems, and I think our memory will be challenged to hold all the information that Vivek shared and other 3 to 4 teams shared with us today. There's so much that we heard. So, firstly, let me thank Vivek for taking time out to share with us 30 plus years of experience building 50 patents on intelligent systems, and more focusing on physical systems has been quite informative. I think especially for people in this group who are more academic oriented and trying to learn, it is very educative. Thank you, Vivek, for this well constructed presentation. Okay, and I would like to thank you. I would like to thank the PALS partner institutes, particularly the sponsors, Rajalakshmi institutions, Savita Engineering College, and Sona College. Dr. Sendel Kumar from Savita College, and then Dr. Abai for their initial keynote address. Sharing how useful this session would be for students, because an upcoming topic is emerging topic, as initially Arun called out, is a deep technology. I think it's very nice of you to also acknowledge PALS efforts in the current COVID time to organize such sessions, and also Dr. Sendel Kumar mentioned about VLab. Thanks a lot for acknowledging PALS efforts in this regard. And also I would like to thank the teams, the 3 teams which came up with a nice presentation. In fact, one team acknowledged a tool from GE for defect detection. I think Vivek would have pleased to hear about GE tool being mentioned in the reverse presentation, right? So that's very thoughtful of the team. Thank you so much, and thanks for all the PALS PMO team, Arun Dev, and all the others who have been behind organizing this show. Back to MC team.
Hope this event has been fruitful and that you all had a great experience. A little progress every day adds up to big results. We request everyone to take the quiz and fill the feedback form before leaving. Thank you. The feedback form is mentioned in the chat box.
I just wanted to say one thing. I really liked your the presentations from the team. I think you addressed the questions I had directly and very, very clearly, and I learned a lot. So thank you.
Good, sir. Thank you.
Shall we take a quick photograph?
I hope we have the teams and the MCs and everybody.
Can you switch on the video, the participants and the guests, the teams, the MCs?
Dr. Sendel Kumar and Mr. Abai Shankar can also join. It'll be nice.
Team SCC, Savita, quickly turn on your videos.
Let's make it quick. Who's taking the picture?
Yes, okay. I'll take it. Okay, thank you.
Thank you.
Thank you. Thank you all. Thank you, Vivek. Have a good day.
Thank you, Vivek.
Thanks. Thanks, everyone. Bye-bye.
I repeat, I request everyone to fill in the feedback form and quiz before leaving.